Hello and welcome to the lectures on state space approach to control system analysis and design. The topic for discussion now is linear quadratic optimal control. Before this, we have seen the pole placement design methods wherein the desired system response is achieved through design of a control that places the pole of the system, closed loop system, at the desired locations. That method is quite effective. However, there are a few drawbacks in that method, a few disadvantages. Selection of closed loop pole locations is very difficult. Even though we say that poles should be placed so that the coefficients of the desired characteristic equations are met. However, we do not know what coefficients should be the desired coefficients. Then other difficulty is that often in physical systems we have constraints on state variables as well as the inputs. In the pole placement design methods, there is no way to include these constraints on state variables and the inputs. Then, as we saw, we were solving one example. In case of MI systems, the multiple input systems, the application of pole placement methods may be quite tedious. And other thing is that we have more number of equations and less than that the unknowns, and we don't have any particular best way to solve the n equations from that. So these difficulties are faced in the pole placement design. In the optimization methods, there is a development. The development of these methods is so as to effectively tackle these problems which are there in the pole placement methods. These methods require in general minimization of an integral performance index, and this index, the performance index, the performance integral, is defined in terms of the states and the inputs, the state vector xt and the input vector ut. The constraints are manifested by weighting the variables, the state variables and the input variables. Now we start from a little backward, from a point which we have seen some time back. The system to be optimally controlled is specified by an nth order state equation, this one. So in case of optimal control, the starting point is the state equations, whereas the pole placement could have been carried out also with the transfer function. The initial time ti and the initial state at the time ti, denoted by xti, these are known, and design specifications are defined for the final time tf and final state xtf, x at time tf, tf being the final time. And an integral performance index is specified to yield the optimal control, given in terms of a functional L which is positive definite. So performance integral is an integration of L, the argument of which are x, u and t, the state, the input and the time in general, integration from initial time Ti to terminal time Tf, the final time Tf, L being positive definite. And the performance is said to be optimal if this Pi is minimum. When this performance integral achieves its minimum value, the performance is said to be optimal. In physical systems, there are constraints, especially on the inputs. The magnitude of input may not be beyond certain minimum and certain maximum. Also, many times there are constraints on the rate of change of the input. For example, the throttle cannot be increased beyond a point, and thereby the rate at which the input can change is saturated. So there are often two constraints. We are only presenting one of them here. The input is to be limited between U max and a U min in physical systems. So there should be some way of accommodating these constraints. Now we come to the formulation of the control problem. Here the objective is to determine the optimal control law, U star, arguments of which are the state and the time, which can do the task of state transfer while minimizing the given Pi. And in general, we have two types of control problems depending upon the performance integral which is there. One is the tracking problem. In these type of problems, a reference is given, denoted by RT here, and an input has to be found out so that the control variable Zt tracks the reference variable. For all t greater than initial time, greater than or equal to initial time, the control variable Zt should be as close to possible to RT, the reference. This Zt may be the state itself, then it is the control problem for the state reference state tracking problem. It can be the output, then it is the output tracking problem, or it can be any other linear combination of state variables. So the variables of interest are represented in Zt, and that Zt has to follow as closely as possible to RT. In fact, theoretically it should be equal to the reference for all time greater than or equal to the initial time Ti. The other one is called as the regulator problem, and in the regulator problem, basically it is characterized by the thing is that RT is generally constant. RT, it is not, doesn't vary with time or varies only very occasionally with time, so that most of the time RT is equal to R0 over long periods of time. And it is required to regulate the variable of interest Z in the vicinity of R0. Zt should be as close to possible to the R0, the fixed set point. So the control is so as to maintain the control variable close to the set point. And again, Zt can be state, so it is a state regulator, or Zt can be the output, So it is output regulator, or it can be any other linear combination of state variables. Now, how to formulate the performance integral or the integral characterizing the performance? So it is selected based on the control problem, and a great care has to be taken so that at the same time we get mathematical convenience in solving the problem, because it is the performance integral which will determine the form of the controller, and it must be feasible to solve the problem for the given performance integral, performance criterion. So it must be selected so as to yield the mathematical convenience. But more important than that is that it should be selected based on the control problem. So both the things are important. Of course, the first one is more important. So in one case, it can be desired, it can be required to maintain the control effort. And then the performance integral may be given by this function, which is a quadratic in the input. U transpose RU. R is a real, symmetric, positive, definite matrix. We have seen when we were discussing stability in the sense of Lyapunov, we had defined the definiteness of a quadratic function, and we know that U transpose RU will be positive definite depending upon the R. So if R is positive definite, then U transpose RU will be positive definite. So one way to specify the requirement is through this one, this PI, in which it is required to minimize the control effort. Now it is very clear that if, because it is a quadratic, its value may not be, it will not be less than 0. It can be only 0. So minimum value will be 0. And one may desire, but then it will not be possible to achieve any control on the state variables or the outputs. So other criterion is to minimize the state deviation, to minimize the states from the desired value of states x0. In case of the tracking problem or regulator problem, x0 can be 0, let us say. It could be t. So it is required to minimize the state deviation from the equilibrium value. So x t minus x0 t, and we assume that equilibrium is at origin. So in that case, pi is x transpose qx. Again, q is a real symmetric matrix. It is required to be at least positive semi-definite. We will see in the subsequent part of the lectures. But it must be positive semi-definite at least. Why? Because if only the input is to be minimized, then the minimum value of input, of course, will be the 0. And so x state cannot be regulated or cannot be controlled. So we have the specification on the state variable given by this performance integral. And often, to be practical, the requirement is specified in terms of both the control effort and the state deviation. This is a more practical approach. The performance integral is sum of a quadratic in X depending upon the weighting matrix Q and another quadratic in U, the input U, which is through this weighting matrix R. And this is called as the quadratic performance index, integral quadratic performance index, and this is more common, more often it is to be used, because there is interest to do both, to minimize the deviation of states from the equilibrium or from the origin, as well as to minimize the control effort. So this PI is often selected. Now with that background, we come to the linear quadratic control problem. We state the problem. Given the linear time invariant system x dot equal to ax plus bu, the task of determination of u so as to minimize the quadratic performance integral between the limits ti and tf is called as the linear quadratic control problem. So this is characterized by minimization of the input determination of the input ut while minimizing this performance integral. That is all about the linear quadratic control. If ti is 0, if initial time is 0 and the final time is infinity, if the two limits are 0 and infinity, then the problem is called as infinite time linear quadratic regulator problem instead of the linear quadratic control problem. Linear infinite time because of that upper limit of integration being infinity, linear quadratic regulator problem from 0 onwards. And the solution of the input ut, we have to determine ut, its solution, this control problem, its solution involves a famous equation called as the matrix Riccati equation, and in the subsequent part of this lecture we devote discussion on the Riccati equation. We will see how it lands and what are the ways for using it, how it is used for designing the control. So we start from the general linear time varying model x dot equal to a tau xt x tau plus b tau u tau. A tau and b tau, we are using the argument time with them, meaning that we are considering the general case of time varying system. So we are given with this system and we have to design the control u tau equal to k tau x tau, and it is to be obtained such that the quadratic performance integral, this we saw a little while back, is minimized. Now the lower limit of the integral is not ti but it is t, which is the present time, and the upper limit is retained as tf, the terminal time, meaning that we are interested the time from now, from now on, and upper limit is tf, meaning that the states will reach the desired value at time tf. Of course, in this q and r are respectively called as the state weighting matrix and the input weighting matrix. So we are interested in this problem, meaning this present time t, meaning from now on till tf in case of the control problem. Now if we impress this control on this system, this u tau we can substitute there. And so the closed loop system dynamics is given by this one. X dot equal to A minus BK X, and that we denote by AC. AC is A minus BK. This is the closed loop system matrix. So when this input is impressed upon the system, the closed loop dynamics is governed by this system matrix AC, which is A minus BK. And the solution to the state of the closed loop system will be obviously the state transition matrix multiplied by the state at time t now, state now. So this x tau, the future value of states for tau greater than equal to time now, will be given by this state transition matrix times xt. This we can substitute in the expression for j, which was there in the previous to this. I am going back to this one. In this one, in place of x tau and x transpose tau, we substitute the values in terms of in terms of phi, the state transition matrix, into xt. And in place of u, we of course substitute k times x. So when that substitution is done, we get this with of course some manipulation, because the j was x transpose tau qx. So this x tau is AC times phi c times xt, the initial time or present time. So this x transpose tau will be x transpose t, excuse me, let me do a little cleanly. So it will be x transpose t will be, x transpose tau will be xt transpose into phi c transpose. So x transpose qx on the left will get x transpose phi c transpose, and on the right it will get phi c into xt, and that k transpose rk comes because we are substituting u equal to kx, and x again becomes phi times x at initial time. So what happens is that x transpose phi transpose on the left and phi into x on the right, they come out common, leaving q plus k transpose rk in the middle. That j changes to this. And we denote that quantity by P. So P is, we go back little. What we are doing is this quantity, this phi c into this quantity into phi, this we denote by P. And because this xt, x transpose t and xt, they do not depend upon integral, they are constant as far as this integration is concerned. So they will come out of the integral sign. So they are out of the integral sign. In between we have p, which is essentially that integral. And this p will satisfy a differential equation which we are going to obtain. This is the solution of a differential equation which we are going to obtain. To obtain that, we first differentiate this expression, this J, with respect to time, of course, initial time. So X transpose Px gives X dot Px plus X P dot X plus X transpose P and X dot. This is by chain rule. We get derivative of this as this. And in that we substitute X dot equal to A times X. X dot T is ACT XT. So that substitution we make. So this X dot T transpose is X transpose into AC transpose. So this is X transpose and AC transpose. Of course the P was there, and this XT is AC into XT. So this XT is out here. So this whole thing gives, by that substitution, upon simplification, X transpose T and XT, they come out common respectively on the left and on the right. In between, we are left with AC transpose P, which comes from here, then P dot, which is here, and P into AC, which comes from this. So we are left with X transpose into this into XT. We hold with this for some time, and we go back to the expression for J, which was integral X transpose QX plus U transpose RU into dt. I have not written the arguments so that it looks simple. Now in this, for this term, in place of U, we substitute, because U was minus kx. So we substitute in place of U minus kx. So this term U transpose RU gives X transpose K transpose RKX. And the whole thing, this thing plus this thing together, X transpose comes out on the left, X comes out on the right, and what is left in the middle is Q plus K transpose RK. So the same expression for J after simplification leads to this expression, and again we can differentiate it with respect to T. So we will get the derivative of J with respect to time T as X transpose tau, because when an integral is differentiated, then it is the same value of the integrand with a minus sign. So dj by dt becomes this whole thing with a minus sign. So we have this expression for the derivative of j, time derivative of j, and we have this expression for time derivative of j. In both, on the left we have X transpose, on the right X. See this, and see this one. On the right X, on the left X transpose. So this derivative will match to the derivative which was there in the previous slide. Let me show. This one, if both are the expressions for the same quantity, then obviously the left hand side and right hand side has to match, and so we get this expression. Just by comparison of the two expressions, we get AC transpose P plus P dot plus P AC equal to K transpose RK plus Q with a minus sign, and we do the change the sides, we get this one. P dot is equal to AC transpose P plus PAC plus K transpose RK plus Q. And this is the matrix Riccati equation which I was talking about in the beginning. And this is also the equation which is the differential equation for the quantity we have already seen. In fact, the solution is known earlier and the equation lands later. This solution was already there in the beginning itself, and we devoted time to derive actually the equation, differential equation, whose solution is this. This differential equation is a famous matrix Riccati equation, and this helps to solve the gain K of the system. So we can note that because Q is symmetric, K transpose RK will be symmetric, and this is pre-multiplied by phi transpose and post-multiplied by phi and then integrated. It is expected to be a symmetric matrix. Other thing we see is that if T is TF, if both the upper limit and lower limit are same, then it has to be 0. So with this condition, taken this as initial condition, we can solve these equations backwards to get this solution. Now we come to using that solution to determine the gain matrix. The derivation will be given in the next lecture, in the next part of the lecture. However, we state the problem along with the solution that we required to determine the K for this time varying system, and that K is to be determined so that this performance integral is minimized. And the solution for K is this, R inverse B transpose P. As I told, the proof is pending. It has to be taken up in the next part of the lecture. And this P is a real positive symmetric matrix, which is the solution of this matrix Riccati equation. It was written little while back. Here we have written without the arguments so that its appearance is simple, and there is a hat over P, meaning that it is the optimal solution. In the sense we want optimal gain. So we will see the proof in the subsequent part of the lecture. However, we summarize whatever we have done so far in this lecture. We have seen how to formulate a quadratic performance index. We have seen the statement of the linear quadratic control problem. We derived the matrix Riccati equation and its solution was seen, and how that Riccati equation gives the solution P, and from the P hat how we obtain the optimal gain matrix, and this gain matrix minimizes the quadratic performance integral, this one, which is selected in the beginning. So thank you very much. We meet in the next part of this lecture to derive this relation for K.